Let's suppose you have a metagenomic dataset with 3 strains. Of course, they are not as nicely aligned in real life. And to make it even more difficult, you only are dealing with small DNA pieces called contigs and not the whole genome. You don't know where each contig is coming from, nor which of them belong together. We can, however, estimate an abundance of each contig, which to a certain extent can be seen as making a normalized frequency table. When 2 contigs come from the same strain, they are more likely to have similar abundances, and the abundance signal is much stronger when you have more than one sample. Our first feature is the abundance vector. Now let's look at what is inside the contig. Contig is a DNA strain that can be characterized by the so-called tetranucleotide frequencies. We simply check for all the combinations of 4 nucleotides or consecutive letters and record how many times each combination appears in the string. Our second feature is tetranucleotide frequencies, or TNFs for short. Now we concatenate the features to create the input for the neural network. If you are familiar with metagenome pinners, for example, VAMP, this is really nothing new. What is new here is the output we are trying to predict. If we had full taxonomic labels for the whole dataset, our work would be simple. We would represent each class as a one-hot label and calculate a cross-entropy loss. But what happens when you run a taxonomic classifier is that your labels are not necessarily down to the species level. Sometimes you get an incomplete one, where the contig was only assigned to a genus or a phylum. A great way to deal with labels that naturally have a hierarchical structure is to use a hierarchical loss. Here I will explain how the most basic one works. It's called flat softmax hierarchical loss and is computed bottom-up. Regardless of its simplicity, it has shown great performance in many applications. In the case of flat softmax loss, the output layer has the same number of neurons as there are leaves in the tree. For our use case, those are species labels. The neural network output logits, which are then transformed into likelihoods using the softmax function, the same as you would do for any classification task. Then we begin to propagate the likelihoods up the tree, assigning each node the likelihood that equals the sum of its children's likelihood. Notice how they still sum to 1 in each level. Now let's see what specific form the flat softmax loss function will take, depending on which label we got. If the label was at the species level, the loss function is the exact same cross-entropy as in any classification task. If the label is only given at the genus level, we then simply ignore that there existed a level below genus and compute the cross-entropy for the nodes on this level. Here we use the fact that they still conveniently sum to 1. And so it continues, able to process labels at any level. Another possible approach would be computing the softmaxes from the top to the bottom. In this case, the likelihoods of the set of children of each node would sum to 1. The one thing that is left to clarify is where the labels come from and what we are training and predicting on. The labels we are training on are in fact the labels we are trying to predict. Well, almost. Imagine that your dataset consists of 7 contigs and each got a taxonomic label from MMSEX or Kraken, you name it. Notice how incomplete they can be. The first thing we do is build the tree structure representing all the possible taxonomic nodes and their relations. The important thing here is that we are not using the entire bacterial taxonomy, but only the labels that come from our particular dataset. We train the network using the context feature as the input and incomplete labels as the output. Then we run the trained network on the entire dataset again to predict the labels. But this time the network is equipped with the knowledge of how the contexts relate to each other, and this information allows us to complete the incomplete labels and even correct the wrong way assigned to us.